And they speak of the Green Bank formula. This was the structure by which scientists would meet in Boca Raton in the National Academy of Sciences in Russia back in '71, hosted 84 of the top scientists from around the world to explore this idea of extraterrestrial life. And they adopted what they called the Green Bank formula, and to try to estimate the number of civilizations in a galaxy capable of interstellar communication. How'd they come to that? Well, R was the average rate at which stars develop during the lifetime of a galaxy. There is presumptions about that by the astrophysicists. The FP is the fraction of those stars that might have planets, and E is the number of those planets per star that were capable of supporting life. Then out of those, there's a fraction of those with life, and then there's a fraction of those that have intelligent life, and then there's a fraction of those planets with intelligent life capable of interstellar communication. The idea is to concatenate those probabilities. And then L is the average lifetime of a society capable of interstellar communication. It turns out each one of those draws upon a different field of science, but by what they concluded after exploring all these things, and you can get the proceedings of this through the MIT Press, and it's fascinating reading because as you can pool what we think we know about the universe, they come to the conclusion that life is an exception. Life, using this kind of an approach, it's clear that the probabilities against it keep concatenating to make life increasingly unlikely. In their words, it obviously is a singularity or a miracle. And there's no other. So from this, it's a very pessimistic conclusion to the probability of encountering extraterrestrial intelligence. And we think that's kind of interesting. But out of all of this kind of thinking, you encounter a thing called the Anthropic Principle. This is a secular term, not one generated by biblical observers. And yet it's what they call it the Anthropic Principle because it appears, as we put everything we think we know about the universe together mathematically, it appears that it was all designed for man. That's why they call it Anthropic Principle. And Paul Davies, a secular scientist of some note, summarizes it seems as though somebody has fine-tuned the nature's numbers to make the universe. The impression of design is overwhelming. His words. It's interesting that in many schools today it's illegal to teach truth, or the existence of design. But the Anthropic Principle, the appearance that the universe was designed for man, and if we put everything we know, what we think we know, together, and we alter it in just the least little bit, life turns out to be impossible. And in fact, some factors as little as 1 part in 10 to the 55th, and life ceases to happen. Let me give you an example. There are only 4 forces known throughout the universe: gravity, electromagnetic force, and 2 nuclear forces, a strong nuclear force and a weak nuclear force. These 4 forces are all that have ever been experienced. Now, gravity, most people understand what that is. That's what causes an apple to fall to the ground, that keeps our feet on the floor. It also binds our solar system together. It keeps the Earth and the planets in their orbits, and it prevents the stars from exploding. That's gravity. It guides the galaxies in their motion. So gravity operates in the microcosm, the small things. It also operates, it's the dominant thing in the macrocosm. Another force that's distinctly different is the electromagnetic force. It's what holds an atom together. It determines the structure of the orbits of the electrons and therefore what molecules make sense. It governs the laws of chemistry, therefore. And it also forms of electromagnetic forces include X-rays, radio waves, light are all in that category. Electromagnetic forces can overcome gravity on the Earth. It can dominate the other forces down to the size of the nucleus of an atom, and there things start to change. We encounter the strong nuclear force that binds the protons and neutrons in the nucleus of the atom. We have the balance between the strong force and the electromagnetic forces that force a nucleus to be something less than 100 protons. That's why a periodic table has essentially 100 elements in it, because of that balance. Energy released by the strong nuclear force is essentially greater than the energy from an electromagnetic force, and that's the chemical forces. Strong nuclear force is why stars shine, and it's also essential for life. There's a weak nuclear force that governs atomic instability and radioactivity, the disintegration of the heavier nuclei. And it can create heat, such as the decay of radioactive materials in the Earth's core or in a nuclear power plant. It's the weak nuclear force that's providing us the energy from that. Well, there's a gravitational coupling that we have always noticed in the universe. If the gravitational coupling was just a little bit stronger, all stars more massive than our sun by 1.4 times, they would burn too rapidly and constantly to maintain life-supporting conditions. So you wouldn't have life if the gravitational coupling happened to be a little stronger. If it was a little bit weaker, all stars would be less than 0.8 times the mass of our sun. There would be no heavy elements. So that all falls apart. The electromagnetic coupling. If it was weaker, molecules for life would cease to exist. If it was stronger, again, molecules for life would cease to exist. See, this is the force that binds the protons in atoms, determines the degree of atomic bonding. And, well, the strong force coupling. If it was slightly weaker, multi-proton nuclei would not hold together. Hydrogen would be the only element in the universe. If it was slightly stronger, nuclear particles would tend to bond together more frequently and more firmly. Hydrogen would be rare in the universe, and the supply of various life-essential elements would be heavier than iron, would be insufficient. The weak force coupling also. If it was larger, there'd be no helium, no heavy elements. If it was weaker, everything would be helium. There would be an overabundance of heavy elements. If you take the ratio of the electron to the proton mass, if it was larger, molecules would not form, life would be impossible. If it was slightly smaller, molecules would not form, life would be impossible. How about the distance from the sun? If we were closer, it'd be too warm to maintain a stable water cycle. If we were further away, it would be too cold to have a stable water cycle. Surface gravity. If it was stronger, the atmosphere would have too much ammonia and methane. If it was like most of the planets in our solar system have. If it was weaker, the atmosphere would lose too much water. The thickness of the Earth's crust, there's over 100 of these, I'm just giving you a sampling here. The thickness of the Earth's crust. If it was thicker, there'd be too much oxygen would be transferred from the atmosphere to the crust. If it was thinner, the volcanic and tectonic activity would be too great. The Earth's rotational period. Don't take that for granted. If it was longer, the diurnal temperature differences would be too great for life. If it was shorter, the atmospheric wind velocities would be too great. So axial tilt was greater, surface temperatures would be too great. And if it was less, the surface temperature would be too great. That axial tilt is what puts it all in balance. Critical factors here. We've spoken of all these different coupling constants, and the distance from the sun, surface gravity, and so forth. Thickness of the crust, the rotation, the axial tilt. The albedo, the reflectivity of the Earth is also critical. A little more, a little less, life would be impossible. The Earth's magnetic field, strangely enough, has to be strong enough to keep the radiation away. The ozone level, this is the one, I love this one, the ozone level. It turns out that if it was just a little bit different, all life would be impossible. Now, let's just take this one as an example. If it's that sensitive, the ecologists like to say, gee, if the ozone layer increases or decreases by a fraction of 1%, cosmic doom occurs. Well, if it's that delicate, who balanced it in the first place? And who is maintaining its balance even today? The CO2 and water vapor levels is the same kind of thing. So evidence in the microcosm. At the atomic and subatomic level, the slightest variation in any of these primary constants of physics, some as sensitive as 1 part in a billion, causes life to be impossible. And when you have that many factors, each of which is that delicate, that all makes life a very, very rare thing indeed, and implies not only elegance of design, but elegance in maintenance to maintain those relationships. And so the more these relationships are, the more unequivocally they reveal both two things: skillful design in their origin and diligence in their maintenance.